Okay, good afternoon, everyone. Let's get started on combinational logic circuit, logic gates, the gateway to digital that allows all magic to happen. All right, let's see. Let's share, record. Well, recording is already on, so we can talk about that after class if you want to. Okay, let's see. So we did all this binary number system, decimal, binary, two's complement, binary addition, subtraction, and now we get into logic gates. All right, so logic gates. Now, we are not studying the actual device physics of these gates, right? You're looking at a higher up picture. Each of these gates is actually built out of transistors, whether they're well, typically not BJTs, but like FETs and MOSFETs, right? So CMOS stands for complementary MOS. MOS stands for metal oxide semiconductor, which is a fabrication technology for a field effect transistor. So CMOS stands for complementary MOS, PMOS, and NMOS transistors. Yes. No, so the battery is just like a regular battery, but it says CMOS because, well, I don't know how it sometimes the names just someone picks some name at the beginning and then it just sticks. But basically what it does is that battery keeps the firmware clock in the clock in the firmware running. So when you first turn on a computer, it has the BIOS, which is the basic input output system, and that has a clock. There's a date. It has some storage. There's some memory that is stored in there. To keep those going, you need a battery, and that battery came to be referred to as CMOS because, well, CMOS is used to create all our digital circuits. So again, just to do a brief, we typically don't study FETs or MOSFETs in this class. I'm hoping to change that in the future. But FETs are a different kind of transistor. It works on the electric field effect, hence the name field effect transistor, FET. And there is a, so basically there are three terminals similar to a BJT, and the operation is a little bit different, but there are two versions. Like a BJT had an NPN transistor and a PNP transistor. You have a N channel and a P channel FET. Now, another technology came after FETs, known as metal oxide semiconductor. So you have a metal layer, there's an oxide insulating layer, and then there's a semiconductor layer underneath, which is part of the gate. And so it came to be known as MOS, MOSFET, so MOSFET. If you have a P-channel MOSFET and a N-channel MOSFET in the same circuit, it's now complementary MOSFET circuit. So CMOS, that's where the word comes from, CMOS. So all of those CMOS circuits are used to build these gates. The NOT gate or a AND gate or a NAND gate can be built out of like just two transistors. Okay, two transistors. Anyway, what we have to look at is the view from above. We are looking at these as building blocks. Okay, so each one of these, we're not concerned with the circuitry in there. That's actually under the purview of digital designers, EE digital designers. So these logic gates, you can use them as building blocks for larger circuits. Okay, and the function of each gate is described by a table known as a truth table, because it speaks true. Well, literally the table, you could also say it's the input output table if you want, because that is essentially what it's doing. So the table lists all possible combinations of the input to that logic gate, and on the right hand side of the table, it lists the output. So a fundamental building block for logic gates or logic circuits is the NOT gate. There are three primary gates that we look at: the NOT, OR, and AND. Okay. The first gate we look at is a NOT gate. It has one single input and is noted by a diode-like arrow, and it's a bubble at one end. I mean, at the arrowhead, tip of the arrow. And that bubble indicates inversion. Bubble indicates inversion. So it's kind of like an inverting amplifier, if you will. Okay, the bubble indicates inversion. Now, if you have taken the lab, the lab is ahead, but many of the circuits that you have seen have a bubble at the input. It simply means that when the input reaches that circuit or that logic gate, it is inverted. So that is what is noted by that bubble. Okay, so if the bubble is not there, if it's simply a triangle like this, then it means something else. It simply means it's a buffer. A buffer would be something like the voltage follower, the op-amp voltage follower. It isolates two parts of a circuit, or it isolates two circuits from each other. So bubble is crucial. If the bubble is not there, it is not a NOT gate. But essentially what a NOT gate does is it takes the input and it inverts it. So if you apply a logic 0, you get a 1. If you apply a 1, you get a 0. And it's only one input, and so it only has two states or two possible states, and that's it. So NOT gate is unique in the sense that it can only have one input. It cannot be more than one, typically. So you can have like two going in there, but it'll still, no, for the most part, you'll just say it's a single input. Yeah, not more than that. So that's the NOT gate. Then we have AND gate. So the AND gate, now we look at like 2 and 3 input gates, but you can design it to be as many inputs as you want. Okay, 2 inputs are the easiest. So this is the symbol for a AND gate. Okay, A and B are the inputs, and C is the output. Okay, A and B are the inputs, and C is the output. So you have 2 bits as the input. So 2 raised to n is equal to 2. That means there are 4 possible states of the input. 4 possible states. You can give 0, 0, 0, 1, 1, 0, and 1, 1. And those are listed right here in the truth table. The function of an AND gate is similar to multiplication. Okay. Though in logic design, in logic analysis, we call that function as AND. So C equals A and B. Okay, A and B. Oftentimes you might hear someone say A times B or A multiplied by B, but that's the mathematical function. Logical function is A and B. So C is equal to A and B. And essentially what it is doing is that logical AND function is a mathematical multiplication. So 0 times 0 gives you 0, 0 times 1 gives you 0, 1 and 0 gives you 0, and 1 and 1 gives you a 1. So a logic AND gate, the output will be high only and only when both inputs are high. Yes. It's a circuit. I mean, if we look at a NAND or a circuit, so it'll look something like this. It could look something like this. One output. Very simplistic representation, but essentially that's what it would look like, possibly. So anyway, that's why I said, don't worry about, you don't want to zoom in too much and worry about circuits, because that is a completely separate course by itself in electrical engineering. So E133, digital design, and then 233. No, it's not. They take it. I think they take it the first time. They take it second year. I'm not certain when they take it. Anyway, what was I saying? Yes, don't get bogged down. I got bogged down. So don't get too bogged down into the circuit design or the device physics of it. So because what you want is, see, as a non EE major, even EE major, sometimes if their job description, whatever job they're doing, is not designing or something, then what you need to know is how to take an off-the-shelf part and build something out of it. And that's essentially what you need to learn as a non-EE engineer. So you already have the part. What can you do with that part? It's like a building block, right? You have a brick. You're not interested in how to build the brick. What you want to know is what you can build with that brick. So something like that. Thank you. That's the one. So the output is high only and only when both inputs are high. Now, when we say high, obviously, so there's also the words we use. Yeah. And now it's legal, so you can talk about it. It's fine. But we also say that logic 1 or high is true, right? 0 is sometimes referred to as false and 1 is referred to be true. So we could say the output is true only and only when both the inputs are also true or false. But essentially what we are saying is it's a multiplication, okay, for a 2-bit AND gate. You can also have a 3-bit AND gate, 4-bit AND gate. A 3-bit gate would look like this. You'd have 3 inputs. Function is still the same. So output D is equal to A and B and C. And the resulting function is still the same. The output is logic 1 only and only when all inputs are high. Okay. For all other inputs, output will be 0. All inputs must be 1. It's the same thing for the other. So for AND gate, that is the true function. That is a true function. So if you're building something like a sensor, like, I don't know, like temperature sensor or something, inside a large piece of equipment, and there's gathering multiple inputs from all places. And if it wants to give an alarm, and you would set the system to, let's say, if the temperature goes above or below a certain point, depending on your application. If the temperature goes above a certain point and you wanted to give an alarm, like a overheating alarm, right? So if the sensor detects it going above a certain temperature, then it flips a switch where the signal goes high. So the signal goes high, it might compare it to another reference signal. And when both inputs go high, it sets off the alarm. That is one kind of application of logic, where you have multiple sensors coming in and you want the system to react based on the state of that input. And that's what logic design is used for. Yeah, that's just one of the simplest applications. But I mean, if you think about it, all of the electronics that are in vehicles nowadays, they're all based on lots of digital logic design, right? So self-driving cars, for instance, if you're driving between two lanes, then it takes a look what's on the left side, what's on the right side. If it's trying to overtake automatically, it needs to check, is there any vehicle behind or on the side? If there is something on the side, maybe it is high, maybe the input signal is 1, then you can't go to the left, you gotta wait. If there's nothing in there, then it's logic 0, then you're safe to move over and then overtake. That's kind of like a logic design. And it's not easy to implement, evident by all the accidents that happen. Okay, so the third and final one is the OR gate. Now, OR gate is a mathematical addition, and we simply just use the plus sign and the plus word. So 2 inputs, A and B, result in an output that is A plus B. So 0 plus 0 gives us 0. 0 plus 1 gives us 1. 1 plus 0 gives us 1, and 1 plus 1 gives us 1. We ignore the extra carry bit. Sorry? Math function, yeah. Oh, binary. Binary. 1 plus 1 is sum is 1 with a carry of 1. With a carry of 1. So 1 is carry bit. We for E major classes, of course, we look at circuits which have a carry bit also. Here, not so much. Yeah. Remember, binary number system doesn't have a 2. You're limited 0 and 1. That's it. So a 3-bit OR gate would look like this. Again, 3 inputs, 1 output. And here the truth table is the output will always be high, or output will always be 1 whenever any single input, any one of the input is high or 1. So output is 1 if any input is 1. Okay, any input is 1. So again, depending on what we need, yes. Yeah, okay, yeah, you're correct. So 1 plus 1 would result in 1, 0. But here for an OR function, we take the carry bit and we just say it's 1. So when you have logic high at both inputs, meaning plus 5 volts, then the output will also be plus 5 volts. So in that bit, we would say it's 1. But you are correct. So in this, we are ignoring the not the remainder, but the 0. The OR function output itself is just the truth table itself tells us that it's 1 plus 1 we take as 1. We don't take it as 1, 0. Now, if you wanted to implement, sorry, go ahead. Yes, it's disregarded. Now, larger systems, right now for the most basic, we disregard it. But when you create a larger system, there is a system in place to actually acknowledge that carry bit and use that in the calculations. Now that's a good point. So I overlooked that. Yeah. So 1 plus 1 is typically 1, 0, but we take for the OR function 1 plus 1 is 1, meaning the output of an OR gate will go high if even a single input is high. So if it's 1 and 1 for a 2-input gate, both inputs are high, so the output is high, because the requirement is that any one of the input should be 1. Again, remember, this is a logical operation, not a mathematical operation. So 1 plus 1 equals 1, 0 is mathematics. This is logical. So logical operations is not the exact same thing as a mathematical operation. There's a whole class of algebra that is invented for this, named after George Boole. It is known as Boolean algebra. Okay, Boolean algebra. So we'll touch a little bit on Boolean algebra. Not a lot, a little bit. But does that answer or clear up confusion? Hopefully. Yes. Yeah. Hold on. You, Jonathan, first. It'll go be high no matter what. Yes. Yes. So that is okay. That's a point. So the symbol for a NOT gate is referred to like this, and it's simply referred to as a NOT. So this bar indicates NOT. So a bar is referred to as a NOT. And if it's B bar, then B NOT. So the bar indicates NOT, or the inverse of the function. So the NOT, I would use, let's see, the same thing I use for like an op amp. It's not exactly logic application, but when we want to, in noise cancellation technology, when you want to invert your incoming input, so you have an input that's coming in, and you want to cancel out that signal as noise, because that's surrounding noise that you don't want. So you take that signal and you flip it, you invert it, and you add it back to that incoming signal. It cancels out, goes to 0. And so that's what it's used for. It's also used when you want to synchronize your digital circuits on a single clock. So all of these circuits that we're running, they all need to, so we are learning about what? These are like 2 bits, right? These are 2 bits. But think about the processors and everything that we're using. Your first 68-bit processors, then 16-bit processors, then 32, now it's 64-bit processors. So 64 lines running all in parallel. You have to keep everything synchronized. And so there is a clock signal that synchronizes everything. The speed of that clock is the speed of the CPU that you use in your computer. So 2 gigahertz processor, meaning the clock frequency is running at 2 gigahertz. It's running that fast. So when you synchronize everything, you want some sort of indicator, whether it's actually going high or going low. So when you invert it, there's a transition that takes place from high to low. And that helps with synchronizing everything everything, and keeps everything running smoothly. That's like the simplest explanation that I can think of. Logic wise, inverter, well, it's used to actually create 2 more kinds of gates. Well, it's used to create a lot of gates, but it's used to create 2 more kinds of gates. There's also a couple of laws that we will see in just a few slides, and that requires inversion. So logic inversion. And so that's another application right there. Yeah, De Morgan. So that was OR, and that's the other application. So if you have a NAND gate, we want to invert the output of an AND gate. We attach the output of an AND gate to a NOT gate. So this is AND, and this is NOT. And so the output of a NAND gate, not AND, is A and B NOT. So this would be pronounced as A and B NOT. A and B NOT. And the truth table for this would be, you have 2 inputs, so 4 states again. And now this time, the output will be high, or logic 1, if even a single input is low, right? It's A and B, and then NOT. So 0 times 0 gives you 0, hence the output is 1. It's to A, B, and then C is equal to A and B NOT. This would be 1, this would be 1, and this would go to 0. So 1 and 1 would be 1, and then NOT would be 0. Is low. Is the exact opposite of the AND gate. So AND gate, all inputs must be high in order for the output to be high. So a NAND gate is 1, 1, 1, 0. Yeah, 1's complement. Well, that's how they would actually take the 1's complement, by using a NOT gate. Yeah, that's the NAND gate. NAND. And then, well, guess what's coming up next? NOR gate. So A plus B NOT. A plus B NOT. So here the truth table would be ABC is equal to A. So you got 0, 0, 0, 1, 1, 0, 1, 1. 0 plus 0 gives you 0. So inverse is 1, 0, 0, 0. So output is high only when both inputs are low. Only when both inputs are low. Oh, sorry. Yes. Right. So OR gate was OR gates right here 0 1 1 1, meaning the output goes high when even a single input is high. For a NOR gate, the output goes high only when both inputs are low. If even a single input is high, then the output goes low. So there are quite a few laws and techniques associated with this. All right, any questions before we talk about De Morgan's laws? So those are the two most fundamental laws that we can use to describe any logic equation and build a circuit from that equation. The reason they are important is because it shows us, I'll wait before proceeding. Okay, so here we have De Morgan's laws. These are for 2-bit, actually 2-bit and 3-bit. So they are important because it shows us that you can build any circuit out of just one function. You can build them all out of the AND or OR functions simply by taking the inverse. So the first one is A and B can be written as a OR function. Okay, so an A and B can be written as A plus B if we flip or invert the inputs. Okay, so A and B can be implemented by an OR function if we flip or invert the inputs. So it would be A, yes, so it would be A naught plus B naught and the whole naught. And that's the application, another application of the NOT gate. Yes. Yes, absolutely. Absolutely. So if I was to just write this, an AND gate, that AND gate A and B would be the same as this. I would have a NOT gate. This is A, this is B, and this is output C. So you would have a NOT gate, A and B. Output of the NOT gate would be A naught, B naught. You would feed them into an OR gate. And the output of that OR gate is again fed into a NOT gate. So this would be A naught plus B naught. And this would become A naught plus B naught, the whole naught. That's the first property. And the second one is an OR function, A plus B, can be implemented as a AND function. So A naught and B naught, the whole naught. Effectively, what it's telling you is you can replace an AND function with an OR function or a OR function with an AND function simply by taking the inverse or the NOT functions. So those are for 2-bit. The 3-bit works exactly the same way. So A and B and C would become A naught plus B naught plus C naught, and then the whole naught. And then A plus B plus C is replaced with an AND function. So A naught and B naught and C naught, the whole naught. I got 15 students in the class. That's a lot. Morning classes, I had less than 10. I should have done a pop quiz maybe. That was a joke. I don't tie performance to attendance. So students are all adults. They can attend or not, it's fine. Does this make sense? De Morgan's laws. Okay. So the second one again is the same thing right here. A plus B is 8 times. So you would, if it's one OR gate, then one OR gate can be replaced with an AND gate, but you'd have to have 3 other NOT gates in there. Okay, that's an application of the NOT gate. But more importantly, what these De Morgan's laws tell us is that we can take any gate and create any other gate from it. So we can use them as building blocks. Now, it is very easy to create a NAND gate. It's very easy to create a NAND gate. And you've been using those for a very long time. Where have you heard the words in consumer electronics? NAND flash, SSDs, flash storage. So those are built out of NAND gates. Excuse me. So then we have XOR and XNOR gates. Okay, XOR and XNOR gates. There are some rules. Actually, before we do XOR and XNOR, let me refer to the rules for the previous gates. So let's see. You can write this and summarize. Actually, let's summarize it individually. And okay, NOT gate. So if you think about a NOT gate, output is equal to NOT of the input, right? So if A is the input, output is A naught. So what happens if you have A and A naught? What would be the output? So it's what? You're correct. It is 0. But let's think about why. How many states can A take? 2. If A is 0, what is A naught? 0 and 1, 0. If A is 1, A naught is, output is 0. So the rule would be that A and A naught, output will always be 0. So if you multiply, or not multiply, if you add the input and along with its naught, output will always be logic 0. And then this is kind of self-explanatory. 2 inverses, yeah, very similar. And then AND gate. So we do A and B, right? A and B. And A and B, look at the truth table. What did we say? Output will go high. Output will go high when both the inputs are high. But at the same time, look at the first one. Output is low when both inputs are also low. So when both inputs are the same, the output is so A times A and A is A. Then A and 1 is also A. A and 0 would be 0. Right. The other laws are like this. A and B can also be written as B and A. And there's associative law. So it's what? Okay. A, B, and C.
In philosophy, we're learning logic. I remember we learned logic arguments that they are on that case. We do like that. parentheses, either or and or.
Oh, okay. Logic is logic, right? Whether it's electrical logic or philosophical logic or computer logic. So in OR gate, a plus 0 is a plus 1. I'll let you tell me what a plus 1 is. A plus 0 is evident. If a is 0, then output is 0. So it's equal to a. If a is 1, then output is 1. So it's equal to a. So a plus 0 is equal to a. What is a plus 1? 1. It's 1. And then let's see. A plus a naught is also equal to 1. Right? Whether a is 0 or whether a is 1, you'll have a 1 in there. And a plus a is equal to a. So if it's 0 plus 0, you get 0. If it's 1 plus 1, you get 1. So a plus a would give you a. So then Morgan's laws. X stands for exclusive. Exclusive OR. An exclusive OR is so called because we take A, B here, and output C, you say A exclusive B, A exclusive addition. We get at the output a logic high when both inputs are different. We get a logic low when both inputs are the same. So this gate will give you a low signal when both inputs are the same. It'll give you a logic high when both inputs are different. If it's a 2-bit, if it's a 3-bit, again, it's a different. And exclusive NOR, XNOR is the exact opposite. So XNOR, you have a AND gate, a NOT gate at the output. And because you have a NOT gate at the output is simply flipped. A, B, and C. And so when this time the inputs are the same, you get a high, 1 and 1, and then you get zeros if the inputs are different. So it goes high when both inputs are the same. The XOR is also known as modulo 2 addition. Modulo 2 addition. Yes, you had a question? Plus in the circle, I always call it as exclusive addition or just exclusive OR. It's not adding the inputs together. It's, oh, you're asking about like the mathematical. There is no mathematical equivalent to that. It's just a logical operation. So the logical operation simply tells us that when both inputs are the same, the output will be low. Whether the inputs are zeros or whether the inputs are ones, it does not matter. It's when the inputs are exclusive, meaning 0 and 1 or 1 and 0, that's when the output will go high. Now, there are applications for each one of those gates, but the primary application, as I said, is by using like NAND gates or NOR gates. Mostly it's NAND gates because NAND gate can be implemented with just 2 FETs. You take 2 transistors and you can create a NAND gate. It's very easy to do. And in terms of fabrication, the straightforward process is always the most convenient and the cheapest to implement. And so when they build a circuit, they always build hundreds of millions and billions of transistors all at once, the same thing, and then they program or design it however they want. And so you have used the gates as a building block, and you can use the NAND gate as well as the NOR gate as a building block to create all other gates. So NAND gate can be used as a NOT, a OR, and a AND gate. If you take both inputs of a NAND gate, tie them together, you get a NOT gate. So to create a NOT gate, you would simply create a NAND gate and just connect both inputs together, which again, as I said, is rather straightforward to do. So the output of this gate will be, let's say C would be A and A NOT, right? As an example. If A is 0, 0, so it's 0, 0, what's the output? 1. If A is 1, 1 and 1 and NOT, output is 0. That's the function of the NAND gate. So this truth table is for the NOT gate, and hence a NAND gate with both inputs connected together can function like a NOT gate. Same thing for the OR gate. The OR gate, again, if we utilize or apply our laws, we can see this is a NOT, this is a NOT, and this would be a straight up NAND gate. So you would get A translated A NOT, B as B NOT, and when you give that as an input to the NAND gate, you get A NOT and B NOT, and then the whole NOT. From De Morgan's laws, we can break this down and we can write it as A plus B, right? A plus B. This would actually become A NOT NOT and B NOT NOT. And thus this gives us A plus B. Let's take a 10-second pause, think over it. Let me know if you have any questions. Any questions? Is the process what? Sorry. No, you don't have to memorize it. Nope. You don't have to memorize it. You can have it in your, you can have some of the things in the equation sheet, De Morgan's law especially. Yeah. But if you think about it, you only have to take a look at the input for every state. I mean, every stage. So you take a look at the input and the output, and then you derive the equation, the logical equation at the final end, the final output. And then you can use De Morgan's laws to actually simplify those equations. Yes, did you have a question? Okay. The AND gate, of course, rather straightforward. AND is the opposite of NAND. So all you have to do is add a NOT gate at the output of the NAND gate. So this gives you A and B NOT, and you perform a NOT operation on there. So this becomes C equals A and B NOT. And this becomes AB NOT NOT, thus AB. So by using one single gate or one single NAND gate, you can create a NOT gate. By using 2 NAND gates, you can create an AND gate. And by using 3 NAND gates, you can create a OR gate. Yes.
So why combine the NAND gate and use the OR gate?
What do you mean? Like, oh, you mean like why go through all the hassle of creating more? So it looks as if you're using a lot more real estate on your semiconductor chip, but in reality, when you try to implement the OR gate, it might turn out that it's like 4 transistors that you need, whereas a NAND gate you might just need like 2. Also, it is easier to actually just build an entire semiconductor device just by using one type of gate. So then there's uniformity along your transistors. So then you don't have to worry about like, so it's easier to build billions of the same thing rather than try to build like multiple different kinds of structures. There's actually programmable chips that you can buy. You write code. It's called hardware design language, HDL. Now it's like VHDL, very, very high speed hardware description language, VHDL. And you can buy microchips. They're known as FPGAs and CPLDs. FPGAs are field programmable gate arrays. And those basically have billions of these gates all in one chip. You write a code and you flash your circuit in there. You can create your own processor by programming it that way. So one of the projects that I did in grad school for one of the classes was we wrote a code to create like a microcontroller CPU or something. I don't remember, it's a long time ago. But you write an entire code and then you take a chip and you program it, you flash it, you flash the code in that chip. So the chip makes all these connections, the different connections, and then it works the way we want it to work. So if there are billions of these on one chip, I can create whatever I want using the same kind. So that's the purpose of this logic design, if that makes sense, right? That's the purpose. CPLDs is complex programmable logic devices, kind of similar function. You'd have the same kind of devices all built at the same time, and then you just program it by changing the software code. So you can erase and reprogram, erase and reprogram, erase and reprogram. And then there's the custom chips, ASICs. Those are basically the processors that we use in everyday devices, the CPUs in our desktops, our smartphones. Those are fixed. Once you design it and you build it, it cannot be changed. You cannot reprogram it to do anything else because the physical structure is already built. Those places, we might have multiple combinations. You might have like an AND gate, an OR gate, OR gate. But even there, circuit designers might use something like this because it might be easier to just create the same transistors and then just wire them up differently. Okay, does that make sense? Yeah. So you just have to build millions and billions of the same brick, but then you use the same brick and create whatever design you want. Oh, billions, literally billions. Yep. I haven't checked recently, but I think it was, oh, we can check right now. Oh, it's about a minute left. Let's finish this up and then look at that. So like the NAND building block, we have the NOR building block. The NOR actually requires more transistors. So NAND is more preferred, but it is possible to implement the same logic using a NOR gate. You can build a NOT gate out of a NOR by doing the same thing. You invert it. I mean, sorry, not invert. You short or tie up the two inputs together and you get an inverter, right? So a NOT gate, the output is, this will be A plus B, sorry, not A plus B, A plus A not. So if you connect it together, actually no, what did I do? It become A. No, what am I doing? You short it together, you get 0, 0. 0 plus 0 is 1. No, 0 plus 0 is 0. So the output goes high. So you get 1. And when both inputs are high, 1 plus 1 is 1, opposite is low. And so it functions like a NOT gate. Let's see. So it's A, and output B here. It functions like a NOT gate. For a OR gate, of course, you take the output of the NOR gate and you connect it to a NOT, and you get A plus B. And the AND gate implementation is the opposite of a NAND. So you have inversion of the inputs first, And the output would be A naught plus B naught, the whole naught. Yes, you had a question? You are correct. A plus A one naught, and then because it will become A naught times A naught naught, and then becomes A times A. And so then we get A naught. Okay. Let's see what it's 201. But let me write out this right here. So for this, output will become A naught plus B naught naught. Change this out. You get A naught naught and B naught naught, which gives you A and B. A and B. Now let me look. How many transistors and latest transistors? So the transistor count right now is about 57 billion. But that is Apple M1 Max. I think the, let's see, what do we have? The Intel Ivy Bridge quad core is about 1.75 billion transistors.
What?
Xeon Sapphire is very different. So it just depends on what processor we are running, what process you're gonna run. Yeah. Yeah, yeah. Different functions though. Different functions.
So they need to set up everything like logic too, like
Uh-huh. Yeah.
billions.
Yeah.
Yeah.
Well, for that, you'd have to take BMED 434 or EE 470, 424. Yeah, he is in there right now. Oh, quiz on Monday on everything we have learned in the last week. So logic design. Again, I'll send out an email, but quiz a little bit. Yes. Yes. The homework is already on there. So it's now due on Sunday night.